Hello everyone, today we're going to spend a little bit more time than 60 seconds to talk about custom modules and HLSL expression. I'm going to cover a lot of topics and zigzag through some useful tools you can use. I also recommend checking out videos from other creators to get more in-depth explanations about HLSL. To make HLSL work in Niagara, there are some specific things to know, but we'll go through them over time inside the sandbox. Every link will be in the description of the video. If you want to learn HLSL, the best place to get visual example is ShadowToy. You can also hop on the Epic Game Dev Community Forum, where you'll find code snippets and small examples. Another great exercise is to try reproducing existing Niagara modules in HLSL and match their behavior. If you succeed, you'll get the exact same result, but with the advantage of being able to modify it directly in code. And it's easier to start when you already have the intended logic in front of you. First, we look at how to convert HLSL into nodes, so the logic makes sense and we understand how to connect everything together. Then we will do a breakdown of the 4 custom modules I made with HLSL together. For our first example, we're gonna watch at the blade effect, the radial one that's already in the sandbox. I believe it's a nice start to connect nodes to actual code. So there's a precise logic on how to tackle this one. I felt like the easiest process is to take each blocks of your code and translate it in nodes. So each part of the math is going to be replaced by a node. Connect each block to their respective output and input. And as you can see, I've commented each block to their HLSL equivalent. So we're gonna break down these 2 lines here and what we need to make them work. So I've made a simple breakdown without any inputs. It's just like the logic. So first we have our steps that we're gonna multiply by the execution index. This will be added to the global rotation and this will make our angle. So you see a float angle equals execution index multiplied by step plus global rotation. And this is our angle. Now we have our radius, that's just gonna be an input. We do the cosine and sine of our angle. So we plug our angle value into the angle of cosine and sine. Then we multiply the result of our cos and sine angle to the radius. So now that you've recreated the logic, you can plug it directly into your code. So here there's like some extra steps that I've added, which are like some if logic. But here we have our angle logic. So here we have our steps, the execution index. We add the global rotation from the input. We plug it into the sine, the cosine. We multiply it by the radius, and then we can output our final position. So now that we understood how to connect HLSL to a node, now we can make our own modules directly in HLSL. I've prepared 4 examples that get progressively harder. For each one, I also created a small effect to demonstrate how useful custom modules can be. Sometimes they won't be reusable, but honestly, if you have an idea, just do it. The first example is going to be orientation to target in wall space. A common problem I had was having meshes and sprites in the same emitter and needing multiple nodes to orient them towards the same target. To stop repeating this routing, I made a module. This module generates a quaternion for sprite or mesh orientation based on a wall space target location. So you just move the target in the level and all the guard rays or beams automatically rotates correctly. You link the target position in Blueprint and that's it. So now that we see what it's doing visually, we can break down the code. The code builds a quaternion that rotates one vector onto another. We start with F, the system's forward axis, and T, the normalized direction towards the target. The dot product, and it will tell us how similar the directions are. The cross product gives the rotation axis needed to turn F towards T. If F and T are almost identical or opposite, we need to make a fallback because the cross product becomes unreliable. So we detect those cases with simple threshold checks. Same direction or opposite direction. For the 180 degrees opposite case, we create a fallback axis using 2 fixed orthogonal vectors, blended to ensure a valid perpendicular direction. Then we build 3 quaternions, the standard rotation, the quaternion for the same direction case, and one for the opposite direction. We blend between them using lerp to avoid branching. And finally, we normalize the quaternion and assign it as the particle orientation. You'll notice I added a debug arrow so you can visually confirm orientation. This already exists, so you can just pull it and use it yourself. There's also a select to switch system axis. It will help you rotate your particle effects faster based on the 3 axes. And that's it for this first example. Now for the next example, this one is a little bit more fun. I made a static bounce module that bounces particle off the ground, and it sets the number of bounce, the bounce height over time, and the length of each bounces. The idea is to take a curve and loop it based on the number of bounces. The horizontal motion increases linearly with age, and the vertical motion is driven by height. We output both the position and the bounce index. So how the code works is the module creates looping bounce motion by splitting normalized age. The direction vector is normalized. We use a geometric theory relation, so all bounces loop and fit exactly into the 0 to 1 age range. We have some restitution. It defines how much shorter each bounce is. We find which segment the current age falls into, and inside that segment, we get its position on the parabola. So if you're lost, let me illustrate everything thanks to these excellent tools. On one side there's Desmos, and on the other side there's GeoGebra. Both are free and they're amazing for visualizing your curves or your math. And I made it with sliders, so it's a bit more interactive. This apps lets you see exactly what the curves are going to do. So here we have multiple curve examples on Desmos. Each example represents a parabola formula. All you have to know is they are all quadratic expression. On the topic of quadratic expression, we already are using that in the sandbox. It's in the arrow section. We had this quadratic Bezier curve that allowed us to define a path that's gonna adapt to both start and end location and adjust its curve and keep the same angle. But let's go back to our curves. Now there's a more complex version in GeoGebra with easing and shaping, but there's also a way to repeat your pattern multiple times, which means that the float curve you make in Niagara is also repeatable, just like the math one. Each of these curves can be used inside Niagara and in HLSL. Of course, it's just to illustrate like the math approach. You can use a float curve, of course, and link into your parameters. It will do exactly the same thing. So in our module, we just evaluate the curve from 0 to 1 in normalized space. 1 minute. There have been a lot of energy put in this video and a lot of editing time. So don't forget to leave a like and subscribe and click that bell notification as well for more insane content. Back to the code, only a couple of lines. So we have the loop body who's gonna determine the segment start, the segment width, and the current bounce number. We then compute the vertical position using the parabola expression. Then we compute the final position and the vertical motion. We get our final output, we get our final position output, which is splitted in 2 parts. First, we have the position that the particle is going to be in, and then we have the index, which will decide at which bounce index the particle is. I added a couple of elements to address the entire effect and how to use it in context. On the left, I also added a small example using linear color. So each bounce is going to be attributed to a different color. Now we're going to jump on the third example. It's a conditional state using normalized age. This module creates 3 phases. There's an ease-in phase, a idle phase, and an ease-out phase. The particle on the left side displays the state using colors for debugging. I'm running this module on the system, but I believe you can also run it per emitter. You can choose to skip or force the particle to play the entire idle phase. So, about the code, all the durations are clamped above 0 to avoid dividing by 0. Each state has a timeline. In, idle, and out, they have their own clock. There's looping versus non-looping idle. There are 3 conditions to trigger the ease out. There's an immediate request, an end of idle, and a system deactivation. And we also compute the correct starting time for the ether to prevent jumps if the idle is skipped. Then we determine which phase we are in, a debug color, and finally normalize everything so each phase takes up exactly 1/3 of our custom normalized age. This lets us use normalized time consistently across curves, regardless of the phase duration. Before we attack the last module, I've been exploring a stronger artistic identity and themes for the upcoming examples that are going to release in February. The categories are going to be light effects, bombs and explosions, and liquids. Some effects will propagate into the earlier examples from the sandbox: arrow, fire, ice, blade, wild. I've also been working on a new long format series. It's called VFX Remake. It's reproducing existing effects and breaking them down while matching a visual target. And of course, I'll keep releasing short formats when I have spare time. A few of them are already in the sandbox, and newer ones are going to be released soon. Alright, for the last example, small disclaimer, there are already techniques like sampling triangle using static mesh, which makes this easier. So I provided this extra setup if you want the normal workflow. But for the other people interested in my setup, I'm going to break it down. So we are going to initialize the data from the mesh we want to reconstruct, instead of sampling it from an existing mesh. With this method, you can transform individual mesh faces however you want, using their IDs as a mask. So for the demonstration, I broke down the array. But what do we need inside our arrays? So each face needs a face center, a face normal, and a mesh forward. So to build our tetra, we generate 4 vertices. These are not rendered, they're just used to compute the face data. We use these 4 vertices to get the face center and normals. We select a face by an ID, so now we need to make the mesh forward align the face normal. Here's the alignment logic. Then, like our very first example, we need a fallback to fix the 180-degree case. If our forward and target are exactly the opposite, we can't rely on the cross product or the dot product. So instead, we pick any axis that's orthogonal to the input. Then we normalize the quaternion, and we're going to be able to start and add our extra feature. Here it's the twist around the normals. So we add the twist rotation around the face normal. It's like a rotating mesh or like a rotating clock. It's spinning while the particle is still facing the right direction. Now we're going to add the quaternion with the twist, and then we're going to add the global rotation to be able to rotate all those faces together. So we multiply the global rotation by the face rotation. This will give us the final orientation that goes to the particle. We will also need to rotate the offset by the global quaternion. So instead of rotating the object in its space, we rotate also the offset vectors by the global rotation. And then it preserves the right behavior for any transform. Finally, we assemble everything, and then we output it to our particle data. So that's it for our last example. Now, there are several things to remember. When it comes to making modules, there's not one way to do it, but there's certainly like a very optimized way to do it. It's possible that my examples are not the perfect solution for your problems, but I hope they did help you in some way to build some confidence and jump into HLSL or even making your own custom modules. Since this is the first time I'm making a long format, I might have missed a couple of spots. So if there's any questions regarding all these modules and code, don't hesitate to send me a message. I'll try to reply within the day. Now, I hope you like the video. There's definitely more incoming on many different topics. But for the moment, that's it for me. I wish you a great rest of the day and happy experimentations.